So we want to know how fast the second hand moves on the clock. How can we use calculus to find this? All right, so remember in example 6, actually I think it's in example 7. Sorry about that typo. So we had the equation for the second hand of a clock. And it was 15 sine of pi t over 30, and then 15 cosine of pi t over 30. And it could be pi over 30 t, of course, because it doesn't really matter with division. All right, so that's right there. And we said 0 is less than t, which is less than 60, because, of course, a parametric equation needs to have a domain. All right, now how fast is the second hand moving is the derivative, right? We learn how fast something is with derivatives. Oops, I'll even tie them together for you. All right, so I need to be able to find, right, the second hand moves. How fast the second hand moves. Which means I need the derivative, which would be dy over dx. But here's the trouble. Dy is not really a function in y, and dx is not really a function, well, I mean, it's not really a function in x. So I need to rewrite these. So dy dt and dx dt, because I have both of them as parametric equations, right? If you look at y, which is right here, oops, I never had my second parentheses there, sorry about that. So there's y, there's x, right there, right? They're not function, y is not a function of x, y is a function of t. So I really need dy dt divided by dx dt. Sorry, that's a division right there. All right, so let's look at y. What's the derivative of this? Well, the derivative of cosine is negative sine, so it'd be negative 15 sine of pi t over 30 times the derivative of the interior, which would be pi over 30. Well, pi and the 15 and the 30 will make a half, right? So let's see what this will be. It'll be negative 1/2 sine of pi t over, well, negative pi over 2, I guess I should say, because I can bring that pi out in front. So let me write that way. Negative pi over 2 sine of pi t over 30, like that. All right, now let's do the denominator also, otherwise it's getting confusing. All right, so, all right, it's 15 cosine of pi t over 30 times the derivative of the interior, which is pi over 30. And again, that'll be pi over 2, which I like because then those will also divide away. And then cosine, so it's cosine of pi t over 30. So we're left with, because the pi over 2's will divide, sine over cosine, which is tangent. So it's negative tangent of pi t over 30. Oh, I just fit it in there. There's our derivative. That's how fast it's going to be moving at any point, right? It's the slope of the line to the tangent to the second hand at any time t. So let me write that down. Right? And it's also how fast the second hand is moving. That's a moves, right? All right, so we learned, right, the slope of the tangent line is how fast things happen. So that's from Calculus 1. Now let's consider what this means as we travel around the clock. So, all right. Y prime, which is dy dt, is how the rate at which the y coordinate changes. So it's the rate at which the y coordinate changes. And then dx dt, which is this guy right here, which is x prime of t, is the rate at which the x coordinate changes. I'm going somewhere with this. So the rate at which the x coordinate changes. Now let's think about that as we think about moving around this clock. So of course we start right here and we move this way. So let's think about the tangent as we're in this first bit, right? Because this will be, remember, of course, over here is t equals 15, down here is t equals 30, over here is t equals 45, and back at the start is t equals 0 or t equals 60, right? Because it makes one full revolution around. So if I substitute a number in between 0 and 15, what will happen, right? What will be my tangent? Well, the y prime, well, my negative tangent. The y prime is negative because we're falling, right? So over in this quadrant, y prime is negative because we're going down. X prime is positive because we're going to the right. So to the right is positive, down is negative. And that means together, if I took y prime, which is this guy, divided by x prime, which is this guy, then the derivative should be negative, right? A negative divided by a positive should be a negative for dy dx. Now let's prove it. Let me go to decimals really quickly. All right, so if I took the negative tangent of, and then I said pi divided by 30, and then I picked values. So I want to pick 5, for example. Oops, times 5, I guess, to make it clear. Notice it's negative, just like I said it would be, right? Oh, here, let me put in another. Let me put in b right here. So let me add a slider for b, and b can go anywhere from 0 to 60. Okay, so let's see what happens. So for the first 15 seconds, negative values. But when I slip past 15, there it is, 15, it's positive. See right there? All right, because why? Let's let, actually, I don't need b. I can just use a. It just occurred to me. I can just do it this way. All right, so in this quadrant down here, see how the tangent's positive? Why is that the case? Well, because the negative sign of pi t over, here, let me do it this way. There. Oh, no, it didn't like me. Copy, paste. There we go. See, there's the sign, and then the cosine, right? They're both negative down here, as opposed to the first quadrant. Look at the first quadrant. When I'm up here, my x value, my x prime, which is right down here, x prime of t is positive, y prime of t is negative. And that means that dy dx, so here's y prime of t. And so then dy dx, which is the ratio of the two of them, will also be negative because negative divided by a positive would be negative. Right, so this is dy dx at t. Okay. I should put the y first because it's y over x, right? So if I take this y value divided by this x value, negative divided by a positive is negative. If I let it grow past 15 seconds, so I'm in quadrant 4 right there, it becomes negative over negative. Why is it negative over negative? Well, because as I grow, right, my time, I'm moving downward in y and left in x. So if you're moving down, that's negative. If you're moving left, that's negative. So in quadrant 4, y prime is negative, x prime is negative, which means that dy dx is positive. Right? Over here in this quadrant, y is growing finally. So y prime was negative, negative, because for both of these sides you're going down, but now we're going to grow. So actually for both of these sides it's going to be positive because we're going up. All right, now x prime is negative here because we're moving to the left. Left is negative, right is positive, which means this quadrant will also have dy dx positive, but this quadrant will have dy dx negative. Fascinating, isn't it? All right, so we're figuring out, and this is just one example, but these derivatives, the pink ones, are telling us the speed at which the second hand is moving around. And its positive and negative sign also gives us more clues about what's happening here. Right? Positive is in these two quadrants. Negative is actually in these two quadrants. And it has to do with the motion, right? We're moving down and to the right. All right, so what does that help us with? Well, we have a definition. When we have a parametric curve, the way to find the derivative is to find the ratio of the derivatives of each part. So you take the derivative of y with respect to t over the derivative of x with respect to t. And if you're thinking, that looks a little familiar, yes, it's because this is one of the ways we develop chain rule, is kind of a similar way of thinking about it. Now remember what that would be. dy dt would be the rate at which y changes. And dx dt is the rate at which x changes. And that formula will be very important for finding the derivative of any parametric equations.